So we're on the corner of Wilton and Knightsbridge. So we're opposite Hyde Park. So this is an extension to the Berkeley Hotel. The Berkeley Hotel is comprised of the existing frame behind. It's a luxury hotel. Things have to be right. And the client, Mayborn, has extended it. If we go down a good few metres and 5-6 metres, so approximately where you're stood, we've got the Piccadilly line. That's running up and down Knightsbridge Road, and that is basically shaking our building. The biggest challenge was to have a building without noise, because it's a hotel, so you can imagine the performance specification is rather stringent in terms of room acoustics.
So this site here is the new Emery Suites block for the Berkeley Hotel. So just behind here we've got the Knightsbridge Road, we've got Harrods just up here, Hyde Park Corner, Hyde Park across the way. It's a very noisy site from an acoustics point of view. We've got the Piccadilly line, we've got the Knightsbridge Road, we've got air traffic, all that going on. But one of the major challenges is from the tube, which generates a lot of ground-borne vibration. So that goes through the ground, and if it wasn't interrupted by these bearings here, that energy would carry up through this steel frame and re-radiate as noise inside the hotel suites as like a low frequency rumble. The trains would be audible. So what we're doing here is we've supplied and designed these spring packs. The idea behind these are tuned to a specific frequency which is aligned with the modes of energy that are coming up from the tube lines, and it's respecting the way that the steel frame itself responds to the vibration. Both those need to be taken into account. So these have been installed and the frame simply sits on top. There's 36 of them around the site on 16 column locations, which you can see here. And they're designed to provide 3 Hz response, which equates to about 30 millimeters compression. So that's what these springs will deliver when the building's complete. One of the big challenges for designing packs like these is because 30 millimeters is a lot of movement from a construction point of view. That's why they're supplied in these housings. So the bolts you can probably see just on the side there, they're actually, the whole pack is compressed in the factory to about 90% of the final load, which means these won't actually compress at all until the load from the columns surpasses that preload, and then the final 10 millimeters movement occurs. So it's very controlled, and for the vast majority of the construction, certainly before the steel frame is rigid enough, no movement happens at all. So effectively it's a solid base. When that final bit of load comes on, the bolts will release and the springs will compress that little bit and the isolation will begin, and they provide a break to the transmission path of vibration, preventing a noise in the hotel above. Okay, so the bolts here, so you can see to this side and it's the same on the other side, they're holding the whole spring pack together and they hold it to about 90% of the load. So the concept is that they stay in exactly the same place, but when that final 10% of load comes on, the springs compress that little bit and the bolts dangle free. Really important points with springs. Obviously you don't want to maintain these, you want to just put them in and forget them for the life of the structure. So the material that springs are wound from, it has to be resistant to fatigue, failure, gradual collapse over the decades that this building will be up. So we design these so there'll be no issue for maintenance inspection for the life of the structure at 100 years. That's the plan. So there's a lot of design effort goes into these to make sure they're going to last without any worry about sort of failure, corrosion, overload, fatigue failure, because there is a vibration quotient here. All these are taken into account. So although those look simple, there's quite a lot of design effort that goes into them. So each one of these has got 1, 2, 3, 4 on this particular location, and we vary the number of springs across the whole site to suit the load. So obviously the corner locations support less load than one of the main columns where most of the building weight is supported. So it varies, and we work closely with the design team to make sure that load is fully understood. There's a lot of unusual load factors when it comes to building isolation we have to take into account. You've got things like gust loading. You have to account for things like terrorist activity, unfortunately, now is a quotient. If something blew one of these columns out, what's the effect on the wider structure? So you have to cater for that. And these are designed to take significant overload. They allow for things like fire. They account for, like I say, sort of bomb blasts, that sort of thing, which can cause huge load shifts. So it's not necessarily the case we just need to know the load. We need to know all the loads that could potentially happen on each location throughout the whole life of the structure. And that's taken into account with the design of these things. So there's nothing can potentially fail or anything like that. They're effectively a fail-safe design.
We've been working with Mason not just with the springs. So we've got this incredible Rogers frame on these spring bearings. because as you can see, we've got a steel box on the top and below is a concrete box. So our point of kind of where we severed the building was at ground floor, and that's where Mason kicked in. They've been responsible in refining the detail with WSP to achieve what's required for the mainframe acoustics. Below ground, don't forget we've got 3 floors of spa. So we're now working to refine box-and-box construction with Mason to complete, a silent spa, which is almost impossible.
My name is Anthony. I'm a site manager for Cormore Construction, so we're the principal contractors for the Emery side of the project. We're managing the structural steel, the facade installation and all the works in the basement. I've been here since December of last year. It's really flown up as far as structural steel stuff as went. It's really been great progress there. Basement's a little bit slower due to some design changes, but it's all balls rolling there now, and we're making good progress. The last month, we've concreted the basement 1, 2, and 3, which is good progress. From Masons. Masons come in, obviously, have done a really good job. So yeah, we're happy with the way things are going.
So Steve Hart and Adam Fox have been helping us with the box-and-box detailing, and they've been doing a tremendous effort. And thank God they exist, because I've learned so much about acoustics. And yeah, big thank you, because they've basically pulled the project together to be able to be in a position where we're on site constructing and giving the client what they want. So you've always got to have flexibility, which I'd say we really appreciate with Mason, insofar as we thought we had we believe we've got most of the detailing done, but again, on site, things don't always go to plan. And so you always need to go back, check things can work, adapt things, and come up with another solution, which is what we've had to do at the moment with this project in regards to just shimming and leveling and tolerances. So the solution's the same, but it's just more the final tweaking of how the system's working in place.
So the guys is working now, is finishing off the floor, the final floor, which is on B3. So he's on the second line of mesh. So he's installed already the Rockall polythene, and then the jacks, and then the rebars. We've done the fourth layer of mesh, and now we'll do the second one, which is the final one. So now we're gonna tie everything, we'll tie the wire, we'll prepare for tomorrow morning.
We are on B3. This is the last pour we are doing on this job. It's the lowest level that we're putting floors in on. I say we're pouring basically almost the entire area of this level of the building, having already done B2 and B1 previously. So we've got about 350-ish square meters of floor going in, and we've got roughly 40 cubic meters of concrete, depending on how the levels and everything work out. So the difference between this level and the previous levels is we are using a slightly different system. So above we use the rubber system, which loads bolts down onto rubber elements, jacks the floor up that way. This one we're using a similar concept with the castings tied into all the reinforcing, but instead uses a spring system. So this makes this allows you basically to have a lower frequency floor. The reason why we require that is not only is this being used as part of the spa and gym area for the whole building, as is the entire basement of this section, but also we are lower down in the building and we're therefore closer to the source of vibration, which in this case is the tube. So the closer you are to the source, generally the more onerous your vibration and isolation requirements become. So in this case, the acoustician wanted to make sure we had a lower frequency system down here, because as you go up the building, that gets naturally attenuated by the sort of structure of physically absorbing. The jacking process for this floor will probably take 3 to 5 days, depending on exactly how it goes. It's going to take a bit longer than the previous levels because they were using a rubber system. You just bang out where they are, pull the rubber bungs out, bolts in, off you go. This system's a little bit different. You have to make sure you take every single lid off, which involves removing a screw, removing the lid. Then you have to take an inner casting out, and then because this floor is getting lifted 100 mil rather than just 50 mil, you have to put a spacer in, then you put your rubber cut back in, then you put your spring back in, and then you put your inner casting then, and then you're ready for the process to start lifting. So even just the preparation process takes a lot longer. Not to mention the fact that the actual lifting itself is a much more physically demanding task. It's more onerous. You have to compress them a lot more even just to get the thing lifting. With rubber, it will start lifting once you've got about 5 mil of compression. These you have to put about 15, 20 mil in before they even start lifting the floor. So yeah, it's a much harder task, and it's a bit trickier in the final to get the final elevation absolutely perfect. But you know, we always get there, and it's not beyond the wit of man, certainly. So yeah, we'll get there. The technical term, we need to achieve at least 20 newtons of strength, which we'd normally expect to achieve, especially in weather like this, within about 3 to 4 days. So in this case, we'll be pouring it on a Thursday. So we'll probably leave it until at least Monday until we start lifting it up, and by then it should be set enough. But it's one of those things where we take a judgment on it. We do it once we know it's ready, basically. Some projects, they require you to take a cube test, which normally will be 7 days, and by 7 days you should have well in excess of 20 newtons. So it either comes down to the engineer's judgment or it comes down to the results of a test. So by the time we've finished this pour today, we'll have finished all our concrete pouring on this job, and we'll have totaled over the 3 floors of a B3, B2, B1, we'll have totaled about 900-ish square meters, which is a good amount to do, quite frankly. It's certainly enough.
So we're minus 6 along this edge, so I think 4's all the way along. So what's happened, we've been across the floor doing a rough level check and just tweaked the jack locations by winding the bolt down another 2 or 3 mil here or 2 or 3 mil there, and then when I'm happy with levels, do a final level check with the rotating laser, and we check probably roughly a 2 meter grid across the floor at the jack locations, and we record that down on our drawing so we can then submit that to the main contractor saying the floor's leveled, it's within tolerance. This one at the moment, it's coming out plus minus 5, which is well within tolerance. It should be, plus minus 10 is a decent tolerance for concrete, but we're well within that at the moment, so it's all looking good. And then once we're happy with everything, I just go over the floor, make sure all the bolts have got some tension on it, so all the rubber elements in the jacks are engaged, and then we basically hand it over to the main contractor to say, right, we finish on that level, slab's now yours.
So we're stood on the scaffolding currently between the refurb of the existing Berkeley Hotel building and then the new building that they're building to the side, where we've got all our gym floors going in and the spring packs and things like that. And on this side, for the build-up, there's a slightly different system. So what we have instead is we have a system consisting of rubber elements with battens and then a whole series of cement particle boards, chosen because they give a similar thickness to plywood, but they're much more dense. So as you can see here, we've got rubber element here, battens, and then we've just got layer, 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 layer. All that's just adding mass to the whole system, trying to make it as stiff and as performant as possible. The challenges on this side compared to the other side are that head height is a lot more restricted. So as you'll see when we go in, there's a lot less from ceiling to floor to work with. So we worked quite closely with both the contractor and with the architects and all the other designers to make sure we had the best system possible, achieving what they needed to achieve, but fitting within a very tight head requirement as well. And that's also reflected in the ceiling design, wherein we had to work with the contractor to fit all of this M&E, all of this air conditioning, all of that kind of stuff in within a very tight frame and still provide an acoustic break. So we've got special low-profile ceiling hangers going in there, just to allow the whole system to work together. This is part of the original structural slab. This might have been an extended piece, but essentially this is just literally on grade. So you just have this, then you'd have probably a screed layer to make it nice and smooth, then you have your thing straight on that. So any vibration, anything that gets into the building itself, just goes straight up through. Especially with an old building like this, they're solid structures. They don't yield too much. They don't have much in the way of structural flexibility. So if you can get the energy in at the right frequency, it will just go straight up through the building. If people are paying a lot of money, they demand the best, and That's what they need to achieve. Then we've got the advantage here of being further up the building, which does, even though this is an old building, very stiff, and it will carry energy up, you will still find that it's, you will get attenuation as you move up, so it will become less and less severe. So that's why we can get away with a different system compared to what we have down there. If we put this in the basement down there, it probably wouldn't be up to task. Whereas here, because we're further up the building, we're much further away from the source of vibration, this system's perfect. So what you can see here is you can see a good cross-section of how all these layers have gone in and gone together. So you can see that they don't line up with each other, and that's by design. Because what you don't want to have boards sitting directly on top of each other like that with the joins, because that creates a weakness in the floor, and it's not as good either structurally or acoustically. So we worked with them closely to make sure that all the boards were staggered like that, so no two joins ever overlap, which gives you the most solid construction and also the best performance acoustically as well. The way this whole build-up has gone, we've got a floor built up to this same uniform level here, and then there's different finishes depending on the rooms. So in the bathroom, for example, there's 30 mil, I think it is, of marble. It's a hefty, hefty construction in there. It's the kind of hotel you're dealing with here. And then in here, there'll be some sort of leveling screed, followed by either a carpet or maybe a wooden floor finish, depending on the exact from room to room. So we have an access panel through the ceiling here, where you can get a better idea of what's going on with the ceiling construction itself. And what we have here, we have a grid of these stiff unistrut channels, then with these top hat sections below. These are what the boards actually physically screw into. So that's what the boards themselves fix up into, and then these are what the hangers interface with. And this is an unusual construction, because normally you'd have the British Gypsum MF system, which consists of much thinner channels here, same sort of channels here, but then you'd have just plasterboard fixed to it. And that kind of system can only take a ceiling of up to about 60 kilos a metre squared, whereas this ceiling is up over 90. This is a very solid construction, and the reason for that being because there's just no head height available. So you can see up here they've squeezed in all the air conditioning, all that sort of stuff, and then they've had the minimal amount of space possible left for an acoustic ceiling, so they wanted the most amount of mass with the appropriate hangers to deal with it. Which is why we've got a slightly unusual hanger up there. We've got our HDB hanger, which is a stiffer hanger, the one you'd normally use for things like large air conditioning units or even other pieces of plant equipment. You know, much more substantial, but it's just necessary for a ceiling like this. So we have those on 1200 by 1200 centres, spaced all the way throughout with this built below. And the ceiling construction itself consists of 3 layers, from memory, of 18 mil cement particle board, and then there's a plasterboard skim on top just to give it that proper nice surface finish that they're looking for. Because you've got all this M&E up here, because as well part of the soffit above is the reinforcing for the concrete beams. So what you've actually, it's not just flat throughout, you've got flat throughout, and then you've got these sort of bits where the structural ceiling actually does this, it sort of dips around and over. So they had to make sure that everything didn't line up, that required revision and coordination and things like that. But we worked closely with them, we were constantly inspecting things, making sure it was done, because the other danger on a job like this is you can't, it's very easy when you've got such a small amount of space to have a solid connection between all the ductwork, which is just fixed rigidly into the soffit. If that touches anywhere on this acoustic ceiling, you're going to be introducing some amount of short-circuiting of that isolation provided by it. So a lot of careful coordination, a lot of inspection on our part. We worked very closely with Piper Hill, who are the fit-out contractor doing this whole section of the building, just to make sure it went in properly, make sure that it was exactly what was needed to be done.
People will be in beds in 2022. I hope so. I hope so. I don't know, otherwise I might get my ass kicked.